Hello everyone, this is lecture 12 of advanced drilling, PTRE 451545. The TA has informed me this morning that he graded the homeworks. I don't know if they're on Blackboard. The grades are on Blackboard. Yeah, but I have the grades. I have the grades here. They are not on Blackboard. I will put them on Blackboard, but like it was 100, 100, 100, 100, 96, 92, 91, 87, 79, 62, and 36. The grades for your class so far.
I received my already. You received your text message. We posted you this morning.
Oh, okay.
Oh, okay. So it's on Blackboard.
Yes.
Okay, good. Okay. If it was, then I will put them. Don't worry about that. So good job on the first homework. The second homework, I think it's better if I review it today. But I think I made a mistake last time. I want to make sure I sent an email to Carlo. I sent him the wrong solution key, and then was trying to find it, and
I don't know. You didn't upload the solution key of this first homework.
no, I haven't yet.
No.
I haven't yet because it was graded last night. Like I saw the grades this morning when I woke up, so I didn't have the time to upload. I need to go there and see if there is anybody who hasn't submitted yet. I will give them a 0 and then upload the solution key. But because I cannot upload it.
Well, I think in web test when you used to upload it before the grades come out. Maybe I forgot.
Yeah. Maybe it happened because there was a test coming. And I wanted you to see it before. Yeah. That's a different story. We might do that with homework 2 or homework 3 if it goes there. But I mean, we are very well with time in this semester so far. So
0.
yeah, I will upload the key tonight. But I mean, if you made 100, it doesn't make a difference. I mean, you might see some step on the solution key. Anyway, last time I made a big mistake on I did draw something wrong on the hydraulic loop. Remember, the hydraulic loop shows both hydrostatic effects, like with gravity, based on, or density, based on the fluid above you, and friction, right? And I said that, let's assume that this is the hydraulic loop. But now I have a different case where there is hole underneath the bit. So I'm breaking gel. In a sense, you need that for the second homework. I have the bit sitting a few feet above the bottom, and it's just jetting. Okay, it's just jetting. It's basically replacing flushing out the old mat, replacing it with new mat. And I remember I told you, okay, we need to draw this extra carrot here, right?
What do you mean by replacing with new mat?
You have mud coming in the drill string,
Oh, yeah.
and then you are just flushing it out. Yeah.
I thought that's the down that is.
Yeah, and I wanted, the one down is gonna come up. That's the goal. Now, I want you to, I told you last time that this would be parallel to this, and that was wrong. And then I did something else that was wrong. I drew the line, the static line, with the wrong slope. I drew the static line like this, I think, but it should be like this. Okay, something like that. Maybe I didn't draw let me do the hydraulic loop better, just to be on the safe side. Okay, it's gonna clear things up for the second homework. So this is my hydraulic loop. And then I have a static, as if when I'm not pumping, just the weight matters. And it's something like this. Okay, now the carrot that I'm gonna draw underneath is gonna be parallel. It should be parallel to this line. Those two lines should be parallel to each other. So this is how it should look like. Generally, the hydraulic loop has both lines on it, the static line and the dynamic line. And this is what I want you to have for the homework. This line is very easy because it's as if you are not pumping, right? It's just the weight, just the density. So it's just one slope based on the density, that's it. Now, the model that we are using in the second homework is like that. It assumes no friction underneath the bit. So it's almost like underneath the bit, there is no movement of the fluid. That's why the lines are parallel. That's why the lines are parallel. We're gonna see the homework now. So the mistake I did was, one, I told you that this is parallel to this, not the case, and then I drew the purple line or pink line, whatever. I drew it wrongly like this. So the slope should be, remember, the slope in this hydraulic loop is feet over psi, not psi over feet. I always get confused with that. Anyway, that looks much more correct. Okay, let's go to homework 2. Here is due next Wednesday midnight. So, background, a vertical well is drilled to 7,000 feet through vertical depth. The drill string was stripped out of the hole to change the worn bit with a new one. The hole is filled with drilling mud of density 10 ppg. The last casing string, which was an intermediate string, was at depth DCSG, okay, the casing shoot depth. During running in the hole, RIH operations at 6,000 feet TVD, the well is circulated to stir up the mud. It's called breaking the gel, you already know that. The bottom hole assembly in BHA consists of 500 feet of drill collars above them. So it's this schematic that I show here. The well is 7,000 feet, the bit is at 6,000 feet. The BHA is at 5,500, and the bit doesn't have any height. I drew it there, but it doesn't have a height. Problem statement. From a hydraulics program utilized prior to RIH running in the hole, the circulating system pressure drops were calculated at 3 circulating rates, 300, 400, and 500 GPM with the following results. These are friction losses, not hydrostatic losses and gains, okay, just frictional losses. And I give you the total and the breakdown on each component. Surface equipment, you lose 36. Inside the drill pipe, you lose 262. Then inside the drill collars, you lose 100. Then across the bit, you lose 500, etc., etc. And then on the annulus, you lose 95 and 83. And it adds up to something like 1100 for 300 GPM. When you increase the rate, everything changes, and it adds up to a bigger value. And then changes again and changes again. Depends on the rate. Now, mud pump output standpipe pressures at the surface. That's basically the total system pressure losses is the pressure that you measure at the standpipe, just like we did with the simulator last time. That 1940 value that we were reading is basically the standpipe pressure, which is basically, that's all the friction that you need to overcome to bring fluid to the surface at atmospheric level throughout the circulation system. The surface pressure on the annulus or casing side choke is 0 atmospheric pressure. That means basically the fluid comes up to the surface at 0 pressure. So basically, that values with the asterisk is what you need to pump them with so that they are able to come up to the surface at atmospheric. Question number 1. Using Microsoft Excel, construct hydraulic loops for each of the 3 circulating rates. I want both the dynamic loop and the static loop. They're just like the green line and the pink line. What is the dynamic bottom hole pressure in PSI and the equivalent mat weight at 7,000 feet through vertical depth for each of the 3 circulating rates? That means I'm asking you, what is basically the EMW at the very bottom of the hole? So the bit stops at 6,000, right? And then you have 1,000 feet of just fluid that is not moving. So you need to add that amount after the bit. So you need to go to the hydraulic loop at the bottom of that carrot, get the pressure there, and then convert that to this, right? And it's EMW, it's not ECD. Question number 3, what would the dynamic pressure and the corresponding EMW at the bit be as the mat flows out of the jet nozzle? So after the mat comes out of the bit, in each of the corresponding circulating rates. This is basically, you go to 6,000 feet, after the mat comes out of the bit, after you lose what you lose in the jet nozzles, what would be ECD, basically, if you are touching the bottom, and you do the same thing. And notice that they are 15 points each, because you need to do for 3 rates. You have a 300 GPM, you have a 400 GPM, you have a 500 GPM. And here you need to make like 3 circulating rates plots. So it's 3 loops.
For the first one, we also have to plot the dynamic to the static.
The static is just a line. Oh, yeah. And the static, how will it vary from one rate to another? Do you think it's going to change from one rate to another?
The static?
The static? I don't think so.
It's
Since
going
we
to
are not
remain the same.
It's the same mat weight.
Yeah.
It's the same mat weight.
Certain,
So it will be the same line, basically,
Yeah.
all 3. So
since we are not.
yeah, it's just the same line. Just make one plot and keep the same line all the time. What would the static and dynamic pressures and the EMWs at 6,500 feet TVD at the top of the drill collar annulus and at the top of the drill collar annulus at 5,500 feet TVD be for each of the 3 circulating rates? So I want the pressure, the static pressure. Static pressure is easy. Here, sorry, what was it? Sorry, 55 and 65, sorry. I want it here, let me show you. 2 points, basically. Here and here. I want you to give me the static pressure, the dynamic pressure, and the EMW, right? So 3 things at those 2 spots. So 3 times 2, 6. Let me see if I read it correctly. Didn't make anything. What would the static and dynamic pressures and EMWs be, I should say be, at 6,500 feet to TVD and at the top of the drill collar annulus 5,500. So you need to basically go, once you have the hydraulic loop, everything is easy. Now, question number 5. Assume that the fracture gradient is 1 psi per foot and that the casing shoe is set at 3,000 feet TVD. What is the EMW at the casing shoe for each of the 3 circulating rates? Will the casing shoe hold okay for each case, or will there be a fracture? So here I have a question for you. It's like, if you want the pressure of the casing shoe, which side of the hydraulic loop are you looking at? Because there are 2 sides, right? The right side and the left side.
You're right. You're
Okay,
looking at the
sure.
case.
Left.
You're looking at the casing. Is it a?
Should be that.
Right side of the YouTube model, but left side of the hydraulic model.
Oh,
Because it's when you come out of the, so you need to look at those pressures at that depth. 3,000 feet TVD. Part B, suppose there is a leak of test running casing, after running casing to 3,000 feet TVD, and gave a static value of 2,700 PSI for the fracture pressure at the casing shoe. So I did my leak of test to tell me the fracture pressure. I get 2,700 PSI. What would the static surface pressure be when I have a fracture, basically? Will the fracture pressure given by leak of test be exceeded in any of the three circulating rates? So this, what will the static surface pressure be is very important. It's going to be very important later on because when we do kick circulation, we'll be looking at the surface not to exceed that pressure, and we'll be calling it a special name, MASP, maximum allowable annular surface pressure. We're going to learn about it later, but basically it's going to be a value that we should not be exceeding. If you exceed that value, you basically have a fracture. So I want you to basically give me what is the surface value that corresponds to 2,700 PSI at the casing. Very easy. Yeah, you need to do it and then you need to find if you are going to have a fracture in any of the three circulating rates. Question number 6. Suppose that by manipulating the pressure on the annulus through the choke, you can hold a 500 PSI constant pressure on the annulus, either statically when the pump is off or dynamically with the pump circulating at any of the three circulating rates. Assuming that the pressure drops indicated earlier by the hydraulics program do not change when the 500 PSI is applied on the annulus side. Repeat questions 1 through 5. So now you do the same thing again that you did in the previous questions, but with 500 on the annulus. So the mat doesn't come out of the well at 0 PSI anymore, and atmospheric. It comes out at 500. Yeah, because you apply 500 on the annulus. So how do you think that would change everything? If I have 500 in the annulus, everything else stays the same. What is going to do to the loop?
You added 500 to the casing side.
Only the, yeah. And then what happens to the rest of the loop? So we say we don't come up at 0 anymore. We come up at 500. Okay. What do you think will do to the whole loop? It's actually very easy.
Maybe someone is doing.
It's very easy because it tells you here that what does it say?
7.
Do not change when the pressure drops indicated earlier by the hydraulics program do not change when the 500 PSI is applied on the annulus side. It's a hint there. The whole loop will shift to the right by 500 PSI. So you get the loop from here and you move it 500 PSI. That question is ominous because this question is ominous because if we make it to module 5, we are going to do managed pressure drilling. And this is the principle on which the biggest mode of managed pressure drilling is based on. Basically, you add pressure on the annulus, and then you use a smaller mud weight. So you gain some advantages by using a smaller mud weight. And then you also use a low pressure, some pressure on the annulus. I'm not gonna say how you apply the pressure on the annulus. It's a big operational question, like they have something called the rotating control device, etc., which is technology related, but you get the idea. That if I add 500 on the annulus, I add basically 500 to my entire hydraulic loop. Okay. If I need to hit 10,000 psi at the bottom of my hole, and for that, if I have 0 on the surface, basically that means I have mud weight of 10 ppg. Okay. If I apply the extra pressure on the annulus, that means I can use 8 ppg mud or something less, right? Which gives me some advantages like low circulations, it makes my life easier in a sense. So yeah, this is the principle on which one kind of managed pressure drilling is called CBHP, constant bottom hole pressure, is based on. And mathematically, the principle is that. Asim, did you get it?
Yes. At least I know how to do it.
Yeah. Question number 7. So basically, for question number 6, you do questions 1 through 5 again, but you have this new situation, which is basically the math doesn't come up at 500. It comes up at, it doesn't come up at atmospheric. It comes at 500. Now, you are still gonna be losing, like in the surface, you still lose 35.8, for instance, 262.8, blah, 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 blah. Okay, from one to another. But you need to make it to the surface with 500 psi, okay? So obviously you need to pump at 1629, for instance. And anyway, so that's about question number 6. Question number 7, frictional losses inside and outside the drill pipe and drill collars are directly proportional to the lengths for a given drill string, drill fluid hole scenario. I think that's understandable. The surface equipment and drill bit pressure drops are independent on the drill pipe and the drill collar lengths. Nevertheless, they depend on the circulating rate used, as you can imagine. So the bigger the well, the bigger the drill pipe, the more the friction, right? That you're gonna have, right? So it's, I mean, if I gave you frictional losses as like 262 psi, I can give you the pressure losses as something like in psi per foot of drill pipe, right? It's not a problem if I give it to you like this. Okay, very nice. So, yeah. After RIH to 7,000 feet TVD with a new bit, normal drilling activity is resumed with the pressure on the annulus side back to atmospheric. Okay, so we went back to 0 on the annulus. Neglecting any mud density changes due to cuttings in the annulus flow, which will increase friction normally, but neglect that, don't worry about that. What would the minimum casing shoot depth be required to prevent fracturing if the fracture gradient is 1 psi per foot for each of the 3 circulating rates? Repeat this question for a fracture gradient of 0.8 psi per foot. So we said last time, we said earlier today that for fractures, which side of the hydraulic loop do I look at?
Left.
The left, the annulus side. Okay, so I need to be looking at the annulus side. Where is the casing shoe? I think it's 3,000. And then calculate the fracture pressure at the casing shoe. I'm giving you 1 psi per foot. So if it's 3,000, it's 3,000 times 1 psi, it's 3,000 psi. Okay. I need to see if I'm exceeding 3,000 psi at that point, anytime, right? At the annulus side, at 3,000 feet TBD of the loop. All the time I need to be looking at that. Yeah, question number 7 is easier than what it looks. Because yeah, and you can basically, you can also, it might be smart to show it actually I explained it wrong. You don't need to, you do not have a casing shoe here. I'm asking you for the casing shoe depth. Sorry about that. And then I saw the solution key. And it was so I'm telling you, this is how you calculate the fracture pressure. I want you to tell me what's the minimum depth I need to set the fracture, the casing shoe, so that the fracture pressure won't be exceeded by the pressure on the loop. Okay, so if I want to set it at 3,000, I want to make it. I want to make sure that if I want to set it at 3,000, it means that my hydraulic loop on the left side at 3,000 feet is not exceeding the 3,000 psi. And you can solve it graphically, actually. You can solve it graphically by adding a line for the fracture gradient on the hydraulic loop. It's much easier. And you'll be surprised at the answer. But take your hydraulic loops, the relevant hydraulic loops, and add a line for 1 psi per foot. And then add a line for 0.8. And see if you have an intersection between the annulus side of the hydraulic loop and these new lines that you are going to draw. Obviously, how is these lines going to look like, the fracture gradient lines?
1 psi.
Yeah. What shape will they have? It's an easy shape, very easy to draw.
Yeah, 1 psi. It should be, yeah,
Straight line.
yeah, straight.
Yeah, add those straight lines and see if you have an intersection between the hydraulic loop and the.
Changing, and this should be equal. That's mean.
Yeah, if they touch.
Yeah.
Yeah, but what side of the hydraulic loop should touch?
The left.
The left side. If the right side touches, you don't care because that's inside the steel, inside the drill string. So you don't care about that. Yeah, that's graphically is much easier. In the solution key, I have it graphically. But you can do it mathematically too. It's an easy answer. Yeah, a lot of those questions are easier than what they look like. But I prefer that you guys start early so that you have enough time to do if you get lost on the plotting in Excel, you have enough time to fix everything. But it shouldn't be that hard of a homework. Any questions of the homework? Okay.
We're still working on it. So next week we will see whether if we have more questions.
You already started working on it?
Yeah, we're just.
Oh.
We are starting.
Yeah. It shouldn't be that hard. It's just, it looks harder than what it really is. So let me know, or Kalu. Kalu didn't go to Houston. He stayed over.
Yeah,
They canceled the
their
flight.
flight. I don't know why they pick groundhog because this year the weather is not bad. Should have picked
Yeah,
maybe
but
Fargo then.
but still, I mean, I was like, I never heard of a flight cancelled or
So he actually didn't cancel, they rescheduled it.
yeah.
So, and in that effect, they'll be missing their flights at
The next one.
Minneapolis. Yes.
Yeah,
They will.
that's the problem with this place. Is like you cannot leave, or you can drive, and then it takes you the whole day.
Yeah.
So the material for the second homework we already covered it. We are done. You know how to do the second homework. Now we're gonna do about the third homework. That will come after. That will come after.
You're already on that.
Well, I want to give the 3 homeworks before the exam, but it is not posted yet, so it's gonna take a while. For it. How about I will post it the day that the next homework is due? Because this homework was supposed to be due on Tuesday or
No.
Monday.
I think it's on Wednesday.
Yeah,
Wednesday,
maybe. to be on
26,
Wednesday.
right?
Yeah, 26.
Yeah.
26.
Oh, Wednesday.
Yeah.
Then you have only on Tuesday to ask all your questions before you submit it.
No. This homework, the homework 2.
Uh-huh.
Now, this one we went over it today,
Uh-huh.
right?
Yeah.
The next homework I will post it on Wednesday,
Okay.
and then that's gonna be due. It should be before spring break for sure, because I want you guys to have all the, and that I might post the solution key before you get the grades for the third homework, because when we go for spring break, you're gonna be studying for the exam. And when we come back from spring break,
Yeah.
we'll be taking one class is gonna be review and then the exam.
Oh,
So,
just like that. We are ending the semester like that.
No,
We're already almost in March.
no,
The
then there
year,
is
we are ending the year.
then there is the project.
Okay, yeah, project.
Yeah, on the second part of the semester to be only 2 homeworks, because there is 2 parts of the project, which are time consuming. That's why I want to get the homeworks out of the way as much as I can, so that, yeah.
So the second one is due on 26. That's going
Yeah, the one that we talked about
Yeah,
today.
that's going to be on Wednesday.
Yeah.
So you only have on Tuesday as to ask any question you have regards to that.
To this one.
Yeah, to this one.
Yeah, but you have also, you can come to my office
Yeah.
and everything, yeah. Anyway, bit hydraulics optimization. Okay, something that you know from the first class, or the undergrads know from the first class, is that the bit hydraulics are optimized in 2 ways. Either to maximize hydraulic horsepower on the bit, or to maximize the jet impact force. These are the 2 ways you want to optimize the bit, the hydraulics. Okay, that's your goal, your 2 possible goals. Okay, this is not applicable if you have a downhole motor, because if you have a downhole motor, you have an external source of energy to the bit, between the surface and the bit. So what we say here is it won't be applicable. You want to maximize, if you want to maximize the hydraulic horsepower of the bit, it is usually achieved by adjusting the bit nozzle diameter to consume 64% of the total pump pressure across the bit. Okay. Now, this is not a hard value. It means like this is average rule of thumb. Okay. It's not like if I ask you how much of the total pump pressure is lost across the bit, if you maximize for maximum hydraulic horsepower on the bit, don't take the total frictional losses times 0.64 and tell me that's the answer. I had some people in the first time I was teaching the class, they need that.
You give us
Yeah, I'm giving you
standard convective.
It's a rule of thumb. It's a rule of thumb, because if you maximize for the jet impact force, it would be about 46. Okay, smaller portion. Okay, that means, remember when I said the the pressure that you lose in the bead jet nozzles is very important because that's used to make hole. That's related to your ROP. That's what I was referring to. That delta P across the bead. Like pressure change across the bead. Very, very, very important. So you will see how these values are, where do they come from, more or less. But don't use them like for an exact answer in thing. So the hydraulic horsepower on the bead is calculated using this equation. And it has a very famous for mechanical engineers conversion factor, 1714 on the denominator. In that case, the Q is in gallons per minute. That's the flow rate through the bead from the active nozzles. You may have nozzles that are plugged. There is also a pattern for nozzles that change diameter from the surface, but it doesn't work very well, that pattern, from what I hear. And delta P bead in PSI is the pressure drop across the bead. That part in the homework 2 that says the pressure losses through the bead nozzles, that's what basically it is. Okay. So this is the equation that you try to optimize. Okay. From there, you can divide that value, that horsepower value, to the square inch, total square inch of the nozzles. So the nozzles are circular, right? And you generally have 3 nozzles on the bead, but you may have 5. You may have more, you don't know. At the surface area of those nozzles, it's a value in inch square, right? The surface, the area, cross-sectional area of the nozzle. You know, if the bead is looking at you like, I don't have a bead here to show, but okay, this is the bead, has nozzle 1, nozzle 2, nozzle 3. This, they have area, right? So take the area, make it in square inch, divide this value by the square inch, and then is what we call in the oil field HSI. Okay? It's basically given by this. This 1.273 conversion factor has everything that you need. It contains the 1714 in it and everything. Well, it contains it implicitly because you have the HHPV input there. But it basically contains the pi that you will need at the denominator and the, so yeah, pi d square and the 4. So it's like, because this is basically pi d square, pi d nozzle over 4. So you don't have this is included here. So this is basically a value to say, okay, this is how I optimize. I know I want this value to be as high as possible, right? To be making ground, make it
Creating hope.
yeah, creating hole, making hole. So this is what I want. And the diameter of the nozzles, usually it's in inches, but usually it's given in 30 seconds of an inch. So if it's given to you in 30 seconds of an inch, and you want to calculate this diameter of nozzles, don't give me, if it says it's 12 30 seconds of an inch, don't write 12 here and do 12 square. You need to do 12 divided by 32, everything square. You know?
I don't get what you say.
Yeah. If the nozzles are okay, let me give you a better number. 16 30 seconds. Okay, 16 30 seconds of an inch. Okay, what value are you gonna put here?
So you square all of them. Yeah.
Yeah,
16 divided by 32 all square.
you take this 16 over 32 is 0.5. Then you have three nozzles. So 0.5 times 3. It's basically.
The number
Huh?
of nozzle.
Yeah. You have a number of nozzles. But in general, what I wanted to say, forget about the number of nozzles. Here, what you will put is basically a value in inch. Okay, not 30 seconds of an inch. If it's 16 over 32, you will put half. Right? Now, if there is many nozzles, and that's going to be the case on your homework 3, you need to find an equivalent diameter. So take this green value, add it all up, and convert it to an equivalent diameter, as if it was like big thing.
You take an average.
Not an average, they are all the same. The average would be the same, right?
So
You take the total area,
Uh-huh.
and then you divide by the number. So you take the total area. We'll see when the homework comes. Don't worry about homework 3 for now. If we combine these 3, we get something like a bigger area, right?
Yeah.
That area has an equivalent diameter. So this is what you will see. I will explain when I'm explaining homework 3 next week. So don't worry about it for now. Homework 3 is gonna be slightly easier than homework 2. Is less time consuming, but you need to do some thinking. Okay. Any other questions on this slide? Those two equations?
Just the G that you were trying to explain that I didn't get. The G
Yeah.
that the diameter. Of the
Yeah,
nozzle.
you see here it says total.
Yeah.
Yeah, it's basically
Is it that we just take one of and multiply by 3? Not like that.
no, you take the area
The area.
and you multiply by 3, and then that area that
Now
you
calculate
multiply
the
by 3
diameter of that.
is pi this a new d square over 4, and then you have to find that new. Yeah, it's basically. I don't want to use the word weighted average, but it's basically you add it all up and then you.
I'm sure we will get an example that will a problem that we can solve.
Yeah, you'll see when we do the homework. The homework is easy. The homework is easy. Okay, so drilling fluid rheology is, you know what is rheology? Is how does a fluid behaves. Just like in geomechanics, we had constitutive model. It told you how does the rock, the solid, changes in regards to stress and deformation, right? We talked in geomechanics in well conditions about you have stress and strain, and those are related to each other, right? And there were like 6 moduli, and you had to have 2 to get the other 4. That it's called constitutive relations or constitutive model. It's like how does stress and deformation interact? For fluids, we have rheology. That is, I apply this stress on the model, I'm getting this flow, this kind of flow. I'm applying this shear stress, I get this shear rate basically of flow. And there are several rheological models, as we call them. Rheology refers to the science and study of the deformation and flow of matter. Flow is the most important word here. It basically tells you that you are dealing with a fluid.
Yeah.
The term is also used to indicate properties of a given fluid, as in math rheology. Now, models the fluid's shear rate, that's how fast it moves, behavior, versus the applied shear stress. How you need to stress it to get this movement, okay? Those two are related. Just like stress and deformation is in geomechanics, these are related, okay? One brings the other. I apply stress, I get movement, right? I need to, when I'm using a rheometer, I make the mat move. I measure how much stress do I need to input for the mat to move at that rate, and that's what basically the rheometer is giving me. We're gonna see that, don't worry. Common terms used to describe rheological behavior: apparent viscosity, marsh funnel viscosity, plastic viscosity, yield point, tau y is indicated, gel strength, etc., etc. Okay. And these are the models, common models that are used for maths. They are not the only models used, but they are pretty common. Okay. So one type is this straight line in the middle. Let's use this. What does this indicate? So this plot has shear rate on the horizontal axis, shear stress on the vertical axis. It tells you to move this much, you need to apply this much stress. Okay, to move this much, you need to apply this much stress. This is the only thing that is saying. Now with the blue line, what the blue line is telling me is that it's linear, proportional. Okay? Linear. If I apply this and I get this, then I double it and I get double that. Something that you need to know that is a little bit counterintuitive. In many other science disciplines, we have the independent variable that we change on the horizontal axis, and we have the variable that changes in reaction, the dependent variable on the vertical axis. Now we have the opposite. We are in these plots, they are the opposite. But these are how it's typically used in rheology. My co-advisor for my master's degree, who's now the chair in Texas, he did his PhD on non-Newtonian fluids. And he was using a lot of plots like that. But the blue line is basically Newtonian, like linear. Okay, very, very simple. It goes proportional. Okay, now what is the slope of this blue line? This slope here.
Change in the yield point over shear rates.
No, does the slope change at all throughout the line?
I don't get the value.
In the value of the slope in the blue line, does it change? The slope of this blue line, yeah, does it change?
I'll give you the definition.
To me,
If it is linear, it doesn't change.
it doesn't, it will going to be remain the same color, it's straight.
Yeah, it doesn't change. Okay, that's why it's Newtonian fluid, it's linear. So it doesn't change. What is the slope here representing? Forget about these equations. I will explain you what does it mean in these equations, but the slope is measuring the viscosity. So the viscosity is staying constant all throughout. I don't care what shear rate it is or what stress I'm applying, I am facing the same viscosity, right? Because it's a Newtonian fluid. The best example of a Newtonian fluid is fresh water, Glycerin under some conditions is a good example.
Yeah.
Why are you laughing? Huh?
I'm talking about the water cannot change. Fresh water.
Yeah, fresh water is very Newtonian.
Yeah.
Very Newtonian. So, this slope is staying constant throughout the model. So we call that viscosity. Some people use mu for the viscosity. Some other people use the Greek word eta for viscosity. And this equation here, tau, is basically the shear stress, that would be tau on the vertical axis. Gamma dot, Greek letter gamma, with a dot on top of it, is the shear rate. The dot means per second, like per time, per unit time. But gamma dot basically means per unit second. And they write an equation here that is tau equals to eta p times gamma second. They really mean here, they use different nomenclature than us. They really mean the shear stress is equal to the viscosity, plastic viscosity, times gamma dot, okay, times the shear rate that I'm inducing. So to get gamma, I need to apply tau, the appropriate tau, which is given to me by basically gamma is equal to tau divided by eta p. That means the higher the viscosity, the harder it becomes to get a big gamma from the same tau, right? Viscosity is working against me. I need more stress to generate a given motion. Right?
Mhm.
Okay. So that's the Newtonian fluid. If I was, this is not my plot. If it was me, I would have put something like this. Nu gamma dot. Okay. That's all you need to know. That's for Newtonian. Okay. What about the next kind of model? Is the Bingham plastic model. Bingham plastic is the same as Newtonian, but it has what we call a yield point. Okay. A good example of that is toothpaste. Okay. Another good example, I think, is ketchup. Why is this the case? No, I'm asking in general.
I don't know.
You increase, you apply this stress, nothing happens, no motion. This stress, no motion. This stress, no motion. You apply this stress, again, no motion, but you apply a little bit more and you get a little bit of motion. And after that, I apply this, I get proportional motion. So I have no motion until I hit the yield point, and after that, I'm facing a constant viscosity. Viscosity stays constant once I have motion. So when I don't have motion, let's just say the viscosity is infinite. But after I get motion, oh my God, like the viscosity doesn't change. It's still the same. So toothpaste, I need to apply some stress to make it move. But after that, it's pretty proportional. Yes.
Like when you are getting the paste out. So let's say when you press it
Yeah.
and it will not move till you get to that point, then it start now coming out and then it will constant.
Yeah. Yeah. Once you get the motion, it's basically Newtonian after that.
Okay.
After that. So it's basically in the graph is Newtonian with a y-intercept. And that's y-intercept is you need to apply at least this much stress to make it move. That's Bingham plastic. Now, power law is a little bit more complex. Okay. uncooked paste of cornstarch and water. Okay, power law. Let's go here. Power law is not only this. Let me clean everything. Right, wrong. This is the power law, which is basically, it's just like Newtonian. It starts, you don't need to apply any yield stress. But the viscosity, the viscosity changes. How does the viscosity changes with shear rate?
Exponentially.
Yeah, but does it decrease or increase?
I think if you look, it increase and then it's sometime and then gets to a point it's decreasing or something.
What is the viscosity here? The slope here, is it higher than the slope here? What happens to the slope? What is the slope here?
Okay.
You go from a big slope to a smaller. So the viscosity is decreasing.
Yeah.
Okay. 1 second. We call this fluid either, well, I will, 1 second, let me just figure out then. I don't want to say something that is not correct, so I need to check my notes so I don't make anything wrong. So this kind of a fluid is called shear thinning, okay? Shear thinning. It means that the more I get it to move, it's easier later to add more motion, right? It's easier to add more motion. But this is not the only kind of power law. You also have this kind. What does that happen now?
So it means it's decreasing from the beginning and then it's like increasing later.
So it goes up. Viscosity increases. So the more I get it to move, it's harder and harder to add more motion, right? So we call this shear thickening. Okay. Another word for shear thickening is dilatant, which is a little bit counterintuitive. And another word for shear thinning is pseudoplastic. Okay, and the equation for that is tau equals to k gamma n. Okay, now I don't have mu in the equation. Why I don't have mu in the equation? Because or eta, because the viscosity is changing.
Like constant.
Yeah, it's not constant, so it cannot be in the equation because it's changing. I have two other constants, k and n. K and n. Okay. Now k is irrelevant to our discussion for now, but n is relevant to our discussion. Okay. Remember that this is a plot of tau on the y-axis, vertical axis, versus gamma on the x-axis, okay, gamma dot. What do you think would be the n for shear thinning fluid? What value do you expect to have n for shear thinning fluid?
It's not 0.
Huh?
It's 0.
You think it's 0?
0 point something. Less than 1.
Why do you?
Less than one greater than
Are
zero.
you just guessing the number? Or what is your reason for that?
Is it bigger than what or smaller than what?
I said less than one greater than zero.
Less than one greater than zero for what? Shear
Thin.
thinning.
Yeah.
So pseudoplastic.
I'm only guessing.
Huh?
I don't know.
So when you have pseudoplastic, this one, n will be, where do I write it here? N is less than one, bigger than zero. Okay. And then when you are bigger than n equals one, you are a dilatant. Right? Do you agree? Do you agree? Do you see it mathematically why it's the case?
No.
If the power, if this power is bigger than one, you'll get a line like this. If this power is half, you're gonna get a line like this.
Oh, yeah.
Now you see it?
Yeah.
Okay. What if it's one? What is a straight line?
Newtonian.
It will be Newtonian.
Newtonian.
So Newtonian is basically tau equals to k gamma. So basically, we had tau k gamma, and before we said that for Newtonian, tau is eta p gamma, right? So basically, k becomes equal to, sorry, the viscosity for or mu for Newtonian, right? That's why Newtonian is so simple. Power law is Newtonian if n equals one, right? And k becomes viscosity, right? You don't see it? You see it?
I have some.
Okay, good. Okay. Now, what about if I have power law with a yield strength? This is very common for drilling maths, actually. Power law and a yield strength. It's gonna be what we call Herschel-Buckley. Okay, is this line on the top? Where was I? I will make it orange. Okay. So I need to apply a stress to get motion. Once I apply stress to get motion, I'm basically having a shear thinning fluid in this case. Or I can have a shear thickening fluid, right? It's not impossible. So I get power law behavior, but above a yield point, right? Examples are quicksand, shear thinning, and gravy, shear thickening.
So,
Yeah.
at what point in drilling will the drilling fluid be behaving like the shear thickening? And then for the shear thinning.
Well, it depends on what kind of fluid you have. Doesn't mean that it's what properties that you mix. It's not like this is models that can describe your fluid, you know? It really depends. I mean, in the homework 3, you're gonna have a power law fluid. Okay, in homework 3. So you're gonna be dealing with this equation here. Okay, now this equation, it's very easy because when you have something like this, then you can ln both sides, and you do ln of tau equals to n something. You can ln both sides and make it to a linear equation, and then I will show you when the time comes for the homework how to do it. I don't want to write something down that is wrong or now we're working on homework 2. We don't need to worry about homework 3. But yeah, you can very easily plot that on a piece of paper, graph it to a straight line, measure the slope and get K, measure N from the line, etc., etc. And then you basically have K and N, you know? Once you have K and N, you basically have the model. Anyway, these are the rheology models, typical rheology models for drilling. Okay, now how do we relate bit hydraulics to that? That's a good question, because this is what we want to do ultimately. Okay, for maximizing hydraulic horsepower on the bit, we have the bit, the horsepower that is lost on the bit, which actually does a real work, right? And HHPX is all other frictional losses. Where you have friction and you have pressure, you have horsepower, right? Because pressure and rate, you are pumping, right? And you're having the pressure losses to friction. So you are using, basically, you are having horsepower losses. So I rearrange this equation a little bit for HHP bit, which is my goal. And then I convert to Q times delta P total divided by 1714. You have seen this equation before. And for HHPX, I have Q is the same Q because I'm pumping at the same rate times delta PX divided by this 1714. The delta PX is all the losses to friction added together. Okay, that is not going to the bit. Everything else that is not on the bit. Okay, now if my model is power law, if my fluid is power law model, then that delta PX can be replaced by KQN. Okay, KQN. It translates basically from the power law behavior. You don't need to know that. You don't need to know that. Take it for granted for now. So I change this delta PX with KQ n plus 1. Why is the plus 1? Because I have NQ from here, and then I have another Q from here. So n plus 1. You see it, right?
Yeah.
Okay, good. Stop me if you have any questions. Now, if I differentiate with Q and set everything equal to 0, basically I do d by dq both sides to get the maximum value, basically. Okay? So if I differentiate this, what do I get? The variable is Q.
Is delta P a function of Q?
Oh, sorry, I mean, sorry, I differentiated, sorry about that. I differentiated this equation. Cannot write. I differentiated this equation. I cannot write that. But this equation, okay. This here, treat Q like X. Okay, you have, this is the what stays because Q becomes nothing. And then this Qn plus 1, n plus 1, the power comes down, and then I subtract 1. That's how I ended up to this equation. Okay, that's how I ended up to this equation. And I set it equal to 0 because where HHP at the bit is maximized is where its derivative turns to 0. Okay, so I move this on that side. I can move this on that side and get rid of the 1714s, and then some other manipulation. Eventually, I get up delta P total equals to K times n plus 1 times delta PX. Remember, K and N you know from your rheological model. Okay, you know easily, like you are going to see in the homework. Then what is the delta px? We already said from before, delta px is delta p total minus delta pb. Is whatever frictional losses is not taking place at the jet nozzles throughout the circulation system. So I replace them with that, and I move the delta p total together with the left-hand side. And basically I end up with this equation, which after some algebraic manipulation becomes this, okay? Now, delta PB is equal to n divided by n plus 1 times delta P total. Delta P total is what we measure on the standpipe to get 0 out of the well. That's what we did on the simulator last time, okay? Okay, let's assume that n is something between, what do you want it to be? 1 and 2. Okay. What would be this? What would be this fraction here? Let me see if I can draw with the mouse. Okay, with the mouse I can draw, but not with the pen. So the pen is bad. So what would be the value here if n is 1?
That's going to be half and the total delta.
Yeah,
total.
half.
Yeah.
What if n is 2? What would be? 1/3? No, 2/3. What is 2/3 as a percentage? 67. That's the 64% I was telling you earlier. That's the 64% on average I was telling you earlier. Okay, now, this is a good thing to remember, n divided by n plus 1 times delta P total, because everything here is values that you know. You measure this before you start the drilling, and you know that from your rheological properties of the mat. So you know this stuff. These are stuff that you know. Okay. Hence, okay, the delta px is 1 divided by n plus 1. So that's what is left. And you don't need to know how it's being derived, but optimal flow rate would be given by this equation. Okay. Optimal flow. There is a long derivation to get to that.
For you in exams, will this, do you need to remember this or?
No, to derive it, no, but I can ask you this, for instance. You know where the mouse is? Yeah. This equation, for instance, I mean, I know in undergrad, we just give them this equation very often. I didn't do it in my class because I knew there was this class coming up where I can show the whole derivation. But this is a common equation that people should know, because your math engineer can give you n, and your driller can give you delta P total. So it's very easy to get. Now, to go from here to here is a little bit of a struggle. Now, if you want to maximize for the jet impact force on the bit, you will end up with something like this. And again, it's a long equation, it's a long derivation, but this is what you end up with. What is the value when n is equal to 1?
That is 1/3.
1/3. What is the value when n is equal to 2?
So that is that's going to be half.
Half. So we said 1/3 to 1/2. What is 1/3 in percentage? And what is 1/2 in percentage? That's the 46% that we were saying earlier on average. Okay. Now the impact force is given by this equation, and I know it's some random conversion factors, but Yeah, it's a long derivation to get here. We need 2 lectures of derivation to get to that. And then the delta px, that is the rest of the losses that are basically the path losses, those that you want to minimize, right? Are given by basically 2 divided by n plus 2. Right? I think you understand how that n plus 2 divided by n plus 2 becomes 1. So you have the good losses, which is the delta p bit, and the bad losses, which is delta px. Okay? And optimal flow rate is given by this equation. And yeah, that's how you relate rheological behaviors to the bit hydraulics. And obviously, that is, oh, we're done with the class already. Yeah, that's a good time to stop as well. So, yeah, don't worry about the derivation of this stuff. But up to the derivation of this one, up to the derivation of this one at the bottom, this here, I think you can follow. After that, I will see if I am able to find some copies of a book that has the derivation. I will put it on the useful documents, on the useful resources folder, but you don't need to know it for exams or homework even, okay? So don't worry about that. I just want you to know the final result in that regard. And this one, the derivation that we saw is pretty easy. Anyway, thank you very much. I will see you next week. Good luck in the homework.
Thank you.
Thank you. Nassim, if you want to meet me earlier today, I can.
We're gonna talk about it on WhatsApp if you want.
Yeah, sure. Okay, see you guys.